All right, good morning. So today we are going to review for that Unit F test. And there are 12 questions and I have 30 minutes. And so we will just see what we get through. Some of these I will probably condense down and not fill in completely. Or I'll use Desmos to say graph them just to make sure I get everything covered. But the first thing is if you have something like this, log base 2 of x plus 3 minus 4, you should know how to graph by hand. And if you can't do that, you should know how to type this into Desmos. And then looking at this, what I know from the x plus 3 is that right here at -3, which I guess you can't really see, bad color, right here at -3, let's see, 1, no, I can't see it. I think I did -2. So ignore the yellow, right here at -3. It's so small. Right there at -3, because of the x plus 3, we are going to have what's called a vertical asymptote. And so I would say for this, x equals -3. It's going to look something like, and I'll show you just to double check. So if I type this in, log, and remember to get that base 2, you go shift underscore, mine's next to the number 0, log base 2 of x plus 3, which must be in parentheses, and then minus 4. So notice there's that vertical asymptote I was talking about. This will never get to -3. And if you're not sure what the vertical asymptote is, if you go to the table and I type in, say, I guess you can't plug in x values, but if I plug in -3, it's undefined. So because it's undefined, that is where my vertical asymptote is. And up and down, that's x equals. So it's x equals -3. My domain will be everything bigger than -3 because it goes to the right. And my range is going to be everything. It goes down forever, it goes up forever. But the smallest it could be on the x is -3, but not including -3. So it'll look something, I'm not even going to try to graph it. Domain would be x is bigger than -3, not including, and the range would be all real numbers. All right. Now describe how changing the parent function. So here's my parent function, f of x, to this new one affects the original graph. Okay, so what if I were to change this to this? So if I start out at x plus 3 and I just change that to x, what happens? Well, if it starts here and it goes to x, this is going to shift 3 to the right. So going from +3 to just x shifts it 3 to the right. So if you're starting with this, going to this one's 3 to the right from that. So I would say it shifts 3 units to the right. And then going from -4, so that shifts it down -4, and then going 7 up from -4. So how far is it from -4 to 7? that would be 11. So I'm going to say it's going to shift 11 up. And so what I'm going to do just to confirm that is I'm going to type this in. Remember, this one's going to have a vertical asymptote of x equals 0. So the original function there we go. I always want to do that for some reason. Log base 2. And then if I change this to log base 2 of just x plus 7, notice from black to red, it went 3 to the right and it went 11 up. Okay. All right, now let's do the same thing with negative 3 to the x plus 1. So if I plot negative 3 to the x plus 1, notice what it looks like. Okay, now let's look at the domain. Looks like domain is all real numbers. Then if I look at the table, so if I play around with it, if I put in 20 or 30, it's a really, really, really small number down there. But if I plug in like negative 10 or negative 11 or negative 12 or negative 13 or negative 14 or negative 15, see, it gets closer and closer to negative 1, but it will never be negative 1. I'm sorry, not negative 1. It'll never be positive 1. Because the smallest number I could put in here, if I put in any number, if I put in 0, that's 3 to the 0 is 1, negative 1 plus 1, 0. And then any other number I put in here, it's going to change that to a fraction. So this will never reach 1. And if you put in the right number, it'll say 1 because it rounds to 1, but it really will never be 1. So the asymptote comes from here. So I would say it has a horizontal asymptote of y equals 1. My domain is all real numbers. And then my range will be everything less than negative 1, but not including. And so to summarize, I wrote it all down. So remember, it had a horizontal asymptote at 1. And it looks something like this, okay? And I'm not going to bother with the graph. You could go to Desmos and get that, including the table. But suppose you wanted to take h of x, and you wanted to shift it 4 to the right and 3 units, up 3 units. What would this new function be? So right now, it hasn't been shifted left or right. So if I wanted to shift it 4 to the right, I'd put this as x minus 4. That's how I shift it 4 to the right. And if I wanted to shift it up 3 units, if it starts at 1, that'd be 1 plus 3, I would say plus 4. That's how I go up 3 units from 1. So that would be my new function. Find the value of $100 deposited for 50 years and in an account paying 3% annual interest compounded quarterly. So the formula was to find out what you get, you take one, oh, already, I'm trying to do this by memory. Try again. To find out what you get, you take the principal times 1 plus r. R is your interest rate, divided by n, which is number of times compounded, to the number of times compounded, number of years, times number of years. So I started off with $100. My interest rate's 3%, that'd be 0.03. It's compounded quarterly, that'd be 4. N would also still be 4. And then how many years? 50 years. So all I need to do is just type this into the calculator and see what I get. $100 times 1 to get my money back, 3% interest, compounded quarterly, still compounded quarterly. I have to put this in parentheses. How many years? 50 years. $445. So the value would be, I would have $445 and about 67 cents. It makes sense with money to round to 2 decimal places, to the 100. It's not bad. It's a long time to leave money though. 50 years. Now, how much money? So now, what is P going to be? And an account paying 4%, so R is 0.04. Annual interest, so N is 1. Oh, no, compounded monthly. Sorry, N will be 12. To have a balance of $1 million. How much money after 30 years? Well, I'm trying to get $1 million. How much money? That'd be my P. My interest rate's 4%, so R is 0.04. Compounded monthly. And then still 12, so same number goes there. 30 years. All right, well, let me think how I want to do this. Oh, that's not too bad. I see. To get P by itself, I could just divide both sides by this. And now P will be by itself. So P equals 1 million divided by 1 plus 0.04, 12 raised to the 12 times 30. All right. Normally I can't do that. Normally there's a variable up here and I have to take the log of both sides. Well, let's go see. $1 million. Wish I had $1 million. 1 million to the 1 plus 0.04 divided by 12 raised to the, and I must put this in parentheses too, 12 times 30. Let's see if this makes sense. How much money, 4% monthly, and you're leaving it in the account for 30 years? Does it make sense that it would be 301,000-ish? That makes sense. You take $300 and almost $2,000, put it in the bank for 30 years. It makes sense that it would get to almost $1 million, if not $1 million. So the answer makes sense to me. So I would say 30,000. $301,795. And I guess you could include the cents, 87 cents. That's how much money you would need to put in the account now to have $1 million after 30 years. Joshua decides to invest $1,000 at 8% interest compounded continuously. Now we know we're going to use this formula. I keep thinking of them wrong. A equals P E R T, PERT. That's how I remember it. So to find out how much you'll have, you take the principal. E is just a number, Euler's number, raised to the rate, and then T for time. So I would say P is 1,000. The interest rate's 8%, so that'd be 0.08. Find the value after 5 years, so T is 5. So all I have to do is plug that in the calculator. Super easy. $1,000 E. You have to use lowercase e, raised to the, and I'm going to put this in parentheses, 0.08 times 5. And it looks to be 1,409 or $1,491. And about 82 cents. Number 6, and this one probably looks familiar. If I give you an equation, you should be able to plug in what they say and answer the question. So on a college campus of 5,000 students, one return from a vaccination 3-day, the spread of the virus can be modeled by this. Y is the total number infected after T days. So how many students will have been infected by the end of 5 days? All of this, and we're not going to make a table, and what happens in the long run, don't worry about. So what happens after 5 days? All they're saying is plug 5 in for T. And then we just write down the answer. So I'm going to plug this in the calculator, and it'll tell me. $5,000 divided by 1 plus 4.999, lowercase e, raised to the -3 times 5 years. And I don't really believe this, but it says 4,999. .99. Oh, I typed that in wrong. It's -0.8. Really hard to see. Okay, a little bit less. 4,580. And you don't count people as 2/3. So you either say 4,580, probably 4,581 would be better. I just put the $sign. You don't count people as money. So I had wrote down a $sign. That makes no sense. All right. So we're on 4,581 people. Next, we have log base A of B equals C. Which expression is equivalent? Remember, you write this base to this exponent equals this. So it's A to the C equals B. So that would be A. That was super easy. Base to the exponent equals your answer. All right, on these, I don't have time to solve them all algebraically, but I do know I could solve all of these graphically. So the first thing I'm going to do is go through and solve them all with the graph. And then if we have time, go back and solve them algebraically. So the first one was 3 to the, and I have to put that in parentheses because they're all in the exponent, 3x plus 5. And the other one is 243 raised to the 4x. And all I need to do is see where those intersect. I got the blue and the black. They probably come together eventually. Oh. Getting closer. That's the only thing I don't like about this method. Sometimes I think algebraically is easier. See, they look like they cross there. Get closer. And then eventually they cross. I don't have all day to do this, so I'm just going to solve this one algebraically. All right. So I think it's much easier sometimes. So you take the log of both sides. Take the log of both sides. So now the exponent could come down. Oh, now what? Oh, I'm making this way too hard. I'm sorry. I bet we could write 343 as the base of 3. 3 to the what power is 243? Let's go find out. So 3 to the 5th? Ah, yep, I was right. 3 to the 5th. Okay, this problem was about to be pretty hard. So instead of doing this, which technically you can do, it's just going to be a lot of work. If I write this as 3 to the 3x plus 5, but then I know that 243 is 3 to the 5th. Way easier. So 243 is 3 to the 5th. Now that the bases are the same, the exponents are the same. So I say 3x plus 5 equals, and then this would be 20x. Subtract 3x from both sides. Divide by 17, and I get x is 5/17. Why was it so hard to find? And we could go to a table and just confirm. If I type 5/17 in there, I get 640. And if I put here a table and I put 5/17, I also get 640. Okay. So in this case, it was probably better to solve algebraically. Now the next one is 4 to the x minus 2 equals 9. Four to the x minus 2, and then y equals 9. So this one's probably easier to solve. Graphically, it's 1.73. And if we have time, I'll show you how to solve that algebraically. The next one is e to the 7x equals 10.3. E to the 7x equals 2.3. So these are super easy if you have Desmos or graphic calculator. I get 0.119. And so to catch you up on what I'm doing, so I typed this in the calculator, then I typed y equals 9. They intersected at 1.73. I typed this in the calculator and y equals 10.3. They intersected at a negative 11, negative 0.119. Number 11, technically I could solve that also using Desmos. It was log base 4 of 10 minus a third log base 4 of x. And we want to know when that equals log base. I need to make a correction on my review. That should say log base 4. You guys don't know how to do different bases. Log base 4 of 1/5. I don't even see it. Oh, that's because it's just a number. I have to put y equals. There we go. There it is. Again, logs are kind of hard because they get closer and closer and you gotta drag and look. Sometimes I get frustrated and just do it algebraically. Which I may have gone too far. And I'm terrible at graphing, so let's just do that one by hand. If you played around in there long enough, you'd get the answer. And again, I'm changing this from a 7 to a 4. So the way I would go about this is first I'd pull the 1/3 up as the exponent. Remember, property of a log, you could always pull that up. Also a property is if you have minus, minus is the same thing as division. Okay. And then, because these are both the same log, I could say 10 over x to the 3rd equals 1/5. So 10 over, okay. Yep. And then cross multiply. That's 50. X to the 3rd. Which remember, x to the 3rd is the same thing as the 3rd root of x. Undo both sides by raising them both to the 3rd power. So x equals whatever 50 to the 3rd is, which makes sense why I gave it up. It's a big number, 125,000. So to confirm that, I go to the table and I type in 125,000, notice that equals negative 1.16. Okay. So here I was at 2,300. I needed to keep going all the way to 125,000, which is why I taught you how to graph or how to solve algebraically and graphically, because sometimes it's frustrating to solve graphically. All right, we have one last one. And this one, you could probably solve graphically again. Log base 2 of x minus 3 plus log base 2 of x. When does that equal 2? And remember, you have to put y equals 2. Hit home to reset my graph. Much easier. 4. The answer is 4. Now, if I were to solve this algebraically, and this would be my last example, it's important to know this. So this plus means multiplication. So I'd say log base 2 of x times x minus 3 equals 2. I just put x with the x minus 3. Distribute. That becomes x squared minus 3x. Change to exponent form. 2 squared equals that. Two squared is 4. Subtract 4 from both sides and get 0. Factor. And you get x is 4 and x is negative 1. Notice this is the answer, which is what I already said by graphing, which took way less time. And we call this extraneous. It is not really a solution. So just in case you get a problem that asks, what does it mean to be extraneous? There you go. Other than that, that's all I have. We are out of time. Good luck on your test and have a good day. Bye-bye.